So now that we've talked at length about Laplace transforms, we need to talk about inverse Laplace transforms. They are going to be the transform that allows us to go from our S space back to T space, so to speak. The math behind it, again, is going to be complicated. I'm not actually going to show you how to compute an inverse Laplace transform directly. Instead, we're really going to think of it as sort of a transformation that undoes one of the existing Laplace transforms that we already know. So we're going to think of them in pairs. So here's how I want to kind of talk about it. If f of t is the function that we started with, that we wind up taking a Laplace transform of, so it has to be, if this function is piecewise continuous, so remember our conditions, it had to be piecewise continuous and of exponential order on some domain, and the domain that we typically were interested in was from 0 up to infinity. All the examples we looked at were t greater than or equal to 0. And it has a Laplace transform that looks like this. So the Laplace transform of our f of t is equal to capital F of s. Then what we want to say is that our lowercase f, f of t, is the inverse Laplace transform of the capital F of s. So basically the argument is if we have a Laplace transform that looks like this, it takes us from, so we apply the Laplace transform to f of t, and we get capital F of s. Then the inverse Laplace transform will look like the inverse of that. The inverse Laplace transform looks like this. The notation we'll use is an L again, but now with an inverse symbol. And we're going to apply that to the capital F of s, and it will spit out f of t. So if a Laplace transform takes us from lowercase f of t to capital F of s, then the inverse Laplace transform will take us from capital F of s back to lowercase f of t. So they're going to basically undo each other, as inverse functions tend to do. So we're going to basically work with these functions in pairs. So we'll work with a bunch of basically f of t functions and f of s in pairs using a table of Laplace transforms. So the table that I'm going to use is in the book. It's in the appendix. I have a copy of it here. I'll just bring up for us to look at. So this is what the Laplace transform table looks like in the appendix. Let me zoom out a little bit. It's 3 pages long. So it has an f of t on the left, and then the capital F of s on the right, the Laplace transform of this particular f. And we're going to basically just use this table to do both Laplace transforms and inverse Laplace transforms. If I want to do a Laplace transform, I go from the left column to the right column. If I want to do an inverse Laplace transform, I go from the right column to the corresponding value in the left column. And that's how we're going to use it. Basically f of t, capital F of s, and we can go back and forth either direction. This is how they pair up. So Laplace transform left to right, inverse Laplace transform right to left. And this thing is 3 pages long. You notice it has a bunch of functions, a bunch more functions. Eventually we get down here to a bunch of stuff that we'll never actually use. And finally at the very end, right here, tucked in here, one of the things we're going to use most often of all are basically taking derivatives. So fn of t, the nth derivative, here's that formula. You'll notice a couple of these other ones appear. This one we derived the other day. We derived this one the other day. We did some sines and cosines, a bunch of these ones back at the beginning, way back here. We did this one. Maybe I think we did t to the n, or we did t or something. I don't know what we did. Maybe we didn't do any of those. We did some trig functions. So there's a bunch in here. It's a really long table, and we're going to, again, treat it as pairs. There's a slightly, so I'm going to provide you with this. It's in the textbook, so you already have access to it, but it's kind of clunky, and it has a lot more stuff than what we're going to actually use. I'm also going to provide you with this one, which is kind of a more compact version that has everything that we'll be interested in using all on one page, and it includes, down here at the bottom, here's f prime of t, so there's what the first derivative looks like. Here's f double prime of t. The only problem with this one is it's not super high resolution, so it gets a little pixelated. I'll try to find a higher quality version of this, but I think it's from another book anyways, so I'm sure there's some copyright issues. But basically it has f prime, it has f blurry double prime, that's what that is. Here's the nth derivative, so it has all the stuff that we're going to need in this one, and it's a lot more compact than that other one. So I'll provide you with both. You can kind of pick and choose which one you're going to do. But the idea is, for this section, for doing Laplace transforms, inverse Laplace transforms, and all the problems that we're going to solve using Laplace transforms, you need to have one of these tables handy. I'll provide them on the exam, but you're welcome, and in fact, I'd strongly encourage you to print one or the other or both out and actually have a physical copy if you have access to a printer. So that way you aren't having to constantly refer back and forth to a PDF on your screen. So again, this is one, the compact version. Here's the slightly longer-winded but higher quality version. And we'll be using those a ton going forward. So I want to just do a few inverse Laplace transforms in the same way that we did the regular Laplace transforms, just so we can all get a handle on kind of how to use that table. So the first thing I want to do is the following. Let's find the inverse Laplace transform. So I want to find the inverse Laplace transform of an f of s that looks like this. Let's do 6 over s squared plus 9. Okay, so the first thing you will need to do if you're dealing with something like this is go to one of our tables. I'll go to the higher resolution one just so we can actually read it. And let me see if I can kind of pull these up side by side. And since this one doesn't cover very much anyways, let's see if I can make this a little more compact over here. Okay. Okie doke. So this is our goal. We want to find the inverse transform of this. What that means is right now we have capital F of S. We have something that shows up in the right column of our table. So I need to scroll through this right column looking for something that looks vaguely like this. So it's a fraction. It has a constant on the top, and it has s squared plus some constant on the bottom. So as we go through this, I run into this one right here that looks kind of suspiciously similar. It has a constant on top, it has s squared plus some constant, in this case a constant squared on the bottom. So it looks very similar, it just doesn't quite match up because I have a 9 right here. That 9 needs to match up to this k squared term, which would mean that k would have to be 3. But I don't have a 3 on top, I have a 6. So it's similar to this one, but it's not exactly. So that's what I want to do though, is note that f of s, in this case, looks similar to the one that we have for, what is this, sine of kt. So it looks similar to the f for sine of kt. And it turns out, if I were to just factor a 2 out and turn this numerator from a 6 down into a 3. So if I were to recognize that I could rewrite f of s like this, I'm going to factor a 2 out and leave a 3 in the numerator. Here's a way of rewriting this. Same thing. Now this piece looks exactly like the f that showed up for sine of kt. And so we just need to be wary of what do we do with this 2? Well, because our original transform, we talked about this in the last video, the Laplace transform is a linear transformation. So sums of things transform. If you take the Laplace transform of a sum, it's the sum of the Laplace transforms. If you have the Laplace transform of a constant times a function, it's that same constant times the Laplace transform of the function. So basically the argument was that if you did Laplace transform of C1 F1 plus C2 F2, you can factor the constants out and do the individual Laplace transforms of the F1 term and the F2 term separately, right? This was true for Laplace transforms. It turns out the exact same thing is true for inverse Laplace transforms, right? If it's undoing this, it's also going to be a linear transformation. So inverse Laplace transforms are also linear. And what that means is we can do exactly what I just said. If I want to take the inverse Laplace transform of our f of s, that's really the same as, in this case, I can pull the 2 outside in this case. So for us, that's the inverse Laplace transform of 6 over s squared plus 9. Well, we just saw that I can rewrite that as 2 times 3 over s squared plus 3 squared. But because it's a linear operator, I can pull any constants that are convenient out in front of that operator. So what we're going to get from this is I'll pull that 2 out, and we're just going to have the inverse Laplace transform of 3 over s squared plus 3 squared. And this is one that shows up exactly in the table. It's this with k being equal to 3. So what is that inverse transform? So what we get from that is going to be 2 times, well, that inverse Laplace transform is, it looks like the sine of 3t. And so that is our inverse Laplace transform. The whole thing that we were starting with, I should have written this here, was we were trying to find f of t. And so we found it. So we get that the original function, f of t, that we were interested in is 2 times the sine of 3t. And this is how we're going to use the table. We're going to basically parse through the table looking for things that look similar to stuff that already shows up in here. And then we will algebraically manipulate it so that it takes the exact form of something in this table, and we will deal with the Laplace transforms, or the inverse Laplace transforms, in that manner. So let's do another one. Let's try this one. So as an example, I want to do, let's find the inverse Laplace transform for our f of s being equal to, I don't know, 5 over s plus 3 raised to the 4th power. Okay, so here's the thing that I need to look for over here in our table. Something close to this. Maybe I can zoom in a little bit. Let's try 125 just so that it's easier for people to see. But this is what I'm looking for. We've got a constant on top, and in the denominator I have a binomial, s plus 3, raised to some power, in this case the 4th power. So that's kind of the one thing I need to look for, is I need to look for a binomial being raised to some powers in the denominator. Here's one that's similar, but it's only raised to the 2nd power in the denominator, so that won't work. But this one is pretty close. It's s minus a to some power. Here I have s plus 3, but I could treat this as s minus a negative 3 if I wanted to, and I could get this form. We're raised to the fourth power. Here that would require, in this, n would have to be 3. And so up here, we'd have a 3 factorial in the numerator. 3 factorial is 3 times 2 times 1, so that's 6. I don't have a 6. I have a 5 instead, but I've got something that's close. I think this might work. So let's try this one. So again, what we recognize, so f of s looks similar to basically the Laplace transform. Let's try to get my notation for the f. So it looks similar to the f for t to the n e to the a t. So I'm suspecting we're going to get something similar to this. So all I need to do is make ours look like this. What was this one? So basically the argument was that the Laplace transform for this one looks very similar. Maybe this would be some good notation that we could use. I want the numerator to be the number, in this case, 3 factorial. So I want a 3 factorial in the numerator. So let's force it to look like this. Let's find a way to rewrite this. So our f of s, which is 5 over s plus 3 raised to the fourth, I can rewrite that as, in the denominator, I'm going to do an s minus a negative 3. We're raising it to, again, the fourth power. But that fourth power is, again, supposed to represent n plus 1, which means n itself must be 3. So that means I need a 3 factorial here in the numerator. I don't currently have that in the numerator, but that means I could factor out a 5 over 3 factorial out in front of this whole thing. So my 3 factorial in the denominator here would cancel the 1 in the numerator here, but now this piece, so I have some constant here, and the remaining piece takes the exact form of this particular part of our Laplace transform table. So that's what we're going to work with. So in this case, what we've basically got is, you can think about it as being, one way to write this is, we have 5 over 3 factorial, that's 6, so 5/6, times, this would be the result of taking the Laplace transform of t cubed e to the negative 3t. Right. Plugging into this form, we've found the Laplace transform that you would get over here if n was equal to 3 and a was equal to negative 3. We would wind up exactly with this. So this piece right here is the Laplace transform of that right-hand side. And our goal is to take the inverse Laplace transform. So what that means is, if we take the inverse Laplace transform of this, if I take the inverse Laplace transform of our big mess, which looked like, where is it? 5 over s plus 3 to the fourth. That's the same as, we can pull the 5/6 out in front again, and we want the inverse Laplace transform of our 3 factorial over s minus negative 3 raised to the fourth power, which we just said, based on this relationship, if I take the Laplace transform of this and I get this, then that means when I take the inverse Laplace transform of this, I should get this. And that's what we're going to get. So 5/6 times t cubed e to the negative 3t. So there's what that result looks like. Okay. So basically, these are not necessarily difficult, but they require some practice. They're definitely something that gets easier with practice. And it's just kind of pattern recognition and trying to match stuff into our table. So let's just do some more of these to, again, get some practice. But think about the types of functions that show up in the differential equations that we encounter normally anyways. There's lots of polynomials, there's lots of exponentials, there's lots of sines and cosines. So we're going to be utilizing a lot of these. Things that involve sines and cosines, things that involve polynomial terms, things that involve exponential terms, and or combinations of those things. So if we come down to the next page, there's lots of combinations of like, here's an exponential times a sine or an exponential times a cosine. We know these types of terms show up in our solutions to our second order, like mass spring system type of problems. So we would expect that we will see and encounter lots of things of this type of form in problems that look like our mass spring system. So use your existing intuition to help kind of guide you, narrow down which type of transforms you should be looking for, or inverse transforms you should be looking for. Okay, and notice I just want to point out, I kind of did these two examples that we've done so far a little bit differently from one another. Right over here, I used the notation that involved a Laplace transform of something that showed up on the left-hand side. So I did Laplace transform of this is equal to the form, right? I made this connection. You don't have to. I never did that up here. You could just say, okay, we're going to force it to look like one of these and just only talk about inverse Laplace transforms the whole way, and then only at the very end, when I've got it narrowed down to exactly something that appears on the right-hand side, do I then make the connection and say, oh, okay, that pairs up with something on the left-hand side. So you can kind of pick the notation that works for you. I think this first way is probably a little bit cleaner. So I'll probably start writing out my problems in this kind of a form for some of the remaining ones. So let's do another example of one of these. So I want to, and if you don't know what I'm talking about, because I feel like I'm sometimes talking circles here, I'm just saying, if you're trying to figure out what you need to write when you're working on these problems, just find something that works consistently for you. I think the way that I wrote this solution up here is cleaner than the way that I wrote this solution down here. So just keep that in mind. That's all I'm saying. So I'm going to try to replicate this approach going forward. So let's say in this next one, we want to find the inverse Laplace transform of f of s is equal to, let's try this one, s plus 1 over s squared plus 2s plus 5. Okay. So this thing is pretty complicated. We can come over here and try to look for things of this form. But in general, we're kind of not going to have a whole lot of luck because there's no generic. Notice our bottom here is a quadratic with like so we have our quadratic term, our linear term, and our constant term. And that's not really how any of these are set up in the denominators. If we look through these denominators, we have some special cases as to the fourth powers here. We have some cases here. This looks close, but it's already factored. So we could maybe try to factor this denominator to get it into one of these forms. But then notice also the numerator has two different parts, and these numerators do not have two different parts. So that's one thing we could try, but that may or may not work. These look similar. They're also going to be quadratics in S. And notice that they actually pair up with the types of, so between these do indeed pair up to types of functions that we see on a semi-regular basis when we're doing our mass spring systems, right? Exponentials times sines and cosines. So this is going to be a form that we're going to commonly want to look for. This isn't there yet, but it might be kind of close. So what I want to do first is kind of think of a way to rewrite this, if at all possible. There's a couple of different things that we can do. So I'll show you different techniques throughout this video, but one thing we can think of is noticing that, like, if I were to say, okay, this looks vaguely similar to these, or even going up here, this is another kind of good opportunity. We could go back to ones that we were looking at over here, even the sines and cosines. Say, oh, this looks kind of similar, right? There's a quadratic in the in the denominator, and we have an function of s on top. That looks vaguely similar. Some of this is close, but it's not quite all there. So let's try to do this problem maybe two different ways and see if we can get it to work out both different ways. So let's start with our f of s. So f of s has a few candidates in the table. So here's going to be approach 1. So let's try to make it look like one of these functions. So maybe like sines and cosines, things that look like s over s squared plus k squared. Can we try to make it look like this? So obviously we can't make it look exactly like this, but one thing that I'll notice is that if I were to rewrite this s plus 1 as a new variable, maybe we could call it r, I can kind of group stuff together here. So let's start with our f of s. And let me just, instead of saying what I'm going to do, let's actually do it. What I'm going to do is I'm going to make this denominator have that same term appeared. So instead of having s squared, I'm going to write the same s plus 1 squared term. But if I did s plus 1 squared down here, I wouldn't get exactly the denominator that I've got here. Instead, I'd get s plus 1 squared. When we FOIL that out, we'd get s squared plus 2s plus 1. So I don't have s squared plus 2s plus 1. I have s squared plus 2s plus 5. But that means that I could rewrite this like this. This part over here is, again, s squared plus 2s plus 1. In the original function, we have s squared plus 2s plus 5. That means I need to add an additional 4 to this FOILed out version of what we've got here. As one option from here, we can say, okay, let's do it like a substitution. Let's call it r. I'm going to let r be equal to s plus 1. And what we're going to basically then have is I have r over r squared plus 4. So what we have now is that this thing is equal to r over r squared plus 4. And again, we just introduced r. It's a shifted version, so we're basically evaluating this. And in fact, to even clean it up a little bit more, let's recognize that that 4 can be rewritten as the number 2 squared, because that's how these k's appear down here. But I've now got something that looks very similar to this cosine term right here, right? Instead of s over s squared plus k squared, I have r over r squared plus some constant squared. So it looks very similar. All we're doing is now evaluating this at the shifted value that r is equal to s plus 1. So it's kind of a shifted value. Well, it turns out that whenever we have a shift like that, there's something that we can use in our table. So the shift, let me write this out. The shift, we've basically shifted our variable. R is just a shifted version of s, right? We've added a constant to it. The shift of r being equal to s plus 1 implies that we'll wind up with an exponential. And this is why. An exponential as part of our answer. And so what is that going to be? Where am I getting this from? Why does that imply that we're going to have an exponential? Well, if I, again, go through the table, down here, where is it? Where is it? Where is it? Here we go. Right here. Line 50. Whenever we're dealing with a shifted version of our function. So in this case, I'm thinking of f as not being f of s, but it's now f of r, where r is equal to s plus 1. You can Laplace transform that back to whatever function corresponds to the f function, but with an extra factor of e to the at. We actually did the reverse of this. We derived going from this direction to this direction in the last video, and we're using that fact here. So basically what I'm suggesting is, instead of thinking of this as f of s, I want to think of it as f of s plus 1, right? Or better yet, f of s minus -1. And f of s minus a -1 will be equal to, according to this table, so if our value of a is -1, oops, missed another parenthesis there, I should get out of this e to the at, so in this case e to the -1t times f of t. So this is the fact that I want to use. This shift, this s plus 1 shift, which I can think of as an s minus a -1, leads to having an exponential times the function that we would otherwise get, where this f of t is just the result of basically this inverse transform right here. So we would get it from that particular piece. Okay, so basically what I'm suggesting is that this gives us the following. So for us, our Laplace transform that we're dealing with, so we want, again, the inverse Laplace transform of, writing it kind of cleaned up, where is it? So it's going to be s plus 1 over the s plus 1 squared plus 2 squared. We can think of this as the shifted version of, so basically, if this is our f of s, we can instead write it as an f of s plus 1, or in this case, an f of r plus 1. I'm just using a different variable because we kind of are switching out. We're not using s. I introduced this r just so that we would have two different variables to work with. But this is basically the same thing as the Laplace transform of r over r squared plus 2 squared, where that r, again, is evaluated at this s plus 1, which is going to cause this type of a shift. So it's going to basically give us an e to the -t times, oops, I forgot my inverse symbol there. So the inverse Laplace transform of, now the unshifted version of this, of what we would get if we were back to just having s's. If this kind of makes sense. Oh, and I missed my inverse Laplace symbol. Okay, here's my inverse Laplace symbol, and we have an e to the -t out in front of it. So basically, the shift that occurred in here, this s plus 1 shift, by converting back to the original variable s without that shift, what we did was we picked up this e to the -t. It's essentially telling us exactly what we've got right here. So if I think of this as an s minus a -1, I could treat it the same as basically doing e to the -t times the Laplace transform of f. So just make it totally clear. If I want the inverse Laplace transform of something that takes this particular form, so of some shifted, of some f of s, in this case, minus a -1, what I'm going to get is the exact same thing. I'm going to get an e to the -t from that shift times the inverse Laplace transform of the original f of s without that shift. So this is the argument that I've made here. I've gone from having a Laplace transform of the version that does have the shift, right? Here's my minus a -1, minus a -1. And by sort of leaping over this one, if you don't want to introduce the intermediate variable r that we're just using to make this shift clear, what I do is essentially pick up this exponential, right? In this case, this e to the -t, and now it's just going to be the inverse Laplace transform of the same function that we had over here, but without that shift, without that +1 added on to the s. And so this is going to be, when it's all said and done, e to the -t. What is the inverse transform of this? Coming back over to our top functions, that was our cosine term right here, with k being equal to 2. So cosine of 2t. So that's one way to do it. That's probably the harder, uglier way to do it. So let me show you another easier way. It turns out we can find something of basically this form in the table if we're careful enough. But this shift thing is going to be a useful thing. So this shift that we just did is where this function is going to come from. And the function that I'm looking for, you'll notice we wound up with an exponential times a cosine in this function. So sure enough, exponential times a cosine, here's the function I'm looking for, and it looks exactly like what we were just talking about, a shifted version of s that we've got right here. It all just looks a little bit different. So in this case, come on, let's zoom in. Approach number 2, which is going to be our nicer approach for most people. Probably prefer to do it this way. Again, so let's just get everything back on the screen so I can make these kind of look similar. So what we want to make it look like now, make it look like, in this case, I want it to be s minus a over s minus a squared plus k squared. And again, that's not hard to do. We did that in this step. So our f of s is going to be, for us, s plus 1 over s plus 1 squared plus the 2 squared. We already figured that out a minute ago. And this looks exactly like the form that we've got here. So basically where a is equal to -1, k is equal to 2. And what does that give us? So when I take the inverse Laplace transform of this mess, s plus 1 over s plus 1 squared plus 2 squared, we can directly go to our table, find this term, and recognize, oh, that's just going to be e to the at, where, again, a in our case is -1. So it's going to be e to the negative t. And it's going to be multiplied by cosine of kt, where, again, k is this term. So that corresponds to this term right here, cosine of 2t. So the much easier way in this case is to go directly to the table. So you can kind of make these things harder than they need to be. The only reason that I did it this hard way first is it's actually how this formula is derived. This formula right here comes from using this idea of a shift that we had derived in our transforms yesterday. So basically using this, you can derive, where is it? This formula. But now that we've got it, do this thing the second way every single time, right? Don't go through all the hard stuff of trying to do a weird shift to get to the answer. Utilize the table as much as possible, but this formula within the table came from using that shift in combination with some of the other stuff that we saw last time. Okay, so let's do another one and see how nasty these things can sometimes start to get. Okay, so now I want to, let's say we want to find the inverse Laplace transform, make that a little nicer looking, the inverse Laplace transform of, let's have our f of s be equal to 3s plus 1 over s squared, come on, s squared minus 4s plus 20. Okay, so the same type of thing here. What we're looking for are often trying to figure out if there's either a way to factor this denominator, or more often than not, what we'll find is these things will wind up being, if you tried to factor them, they would have complex roots. And so we can't actually factor them. But if you were to use the quadratic formula on this to try to find the roots, you'd find that they are actually complex. And so we can kind of determine when that's going to happen, but it's going to happen a lot because that's the type of thing that leads to these scenarios that we're looking at right here, where we wind up with some combination of maybe exponentials plus especially sines and cosines whenever we wind up with complex roots for our denominator here. So in this case, I want to just point that out. This term is going to have complex roots. When it's going to have complex roots, we are essentially telling us we know it's going to involve sines and cosines, and everything that involves sines and cosines means we need to try to get it into one of these forms because we know sines and cosines correspond to these, and or down here, sines and cosines with exponentials. That's another thing that shows up a lot. So something that looks like this. We should be able to write this one right here in a very similar way. Notice this is exactly what happened on the one that we just did. This one itself also would have complex roots. And here is how we basically kind of completed the square on this thing to force that term out. So we're doing the exact same thing here. But just keep that in mind. Whenever you see this term having complex roots, the goal is going to be to complete the square and make it look like we just did in that last problem. Because by completing the square, we'll get it into one of the forms of one of these terms over here that involves having sines and cosines. Okay, so that's our goal. So let's first algebraically manipulate this. So our f of s looks like, let me just copy it down once. So s squared minus 4s plus 20. But we know we want to fix up this denominator. So I'm not going to touch the numerator yet. Let's just stick with 3s plus 1. But how can I complete this square? Well, I know it needs to be s minus 2 squared. Because when you complete the square, really this is the term that tells you how to complete it. So in general, if I'm trying to complete a square, and it looks like something like this, s plus a, and we're squaring it. What you get out of that is s squared plus, right, so if you foiled this out, maybe let's do it totally explicitly, just because people are out of practice. S plus a times s plus a, so this is just our side note that I'm going to erase in a minute. But what do we get when we actually multiply those out? We'll get s squared, so that's this term times this term. Then I'll get an sa plus another sa, so I'll wind up with 2 total a's times s's. And then lastly, we'll get plus a squared. Comparing this form to what we've got right here, it tells us what our a needs to be. We can determine what the a needs to be based on this piece. The plus some constant at the end, it may not be 20. That's the whole point of having to complete the square. But we can always add in some extra constant if need be. We'll add in some other b squared term over here if necessary to make it look identical to what we've got here. But the one thing that we can't control is this coefficient of the linear term, of the s term. So here, that coefficient was a -4. I need to match that up to this plus 2a, and it tells me that in this case, the a has to be a -2. That would make this coefficient be the same -4 that I've got up here. And that's how we found the -2 right here. So the way that I jumped from this to knowing that it was going to need to look like this, knowing immediately that it was going to be this -2 here, all you need to do is basically take half of whatever this coefficient is right here. And that should be basically your a term based on the general form here. So what will I get out of this? When we actually FOIL this one out, we will get, again, we'll get s squared, we'll get -4s, and then the last term is the a squared term, which is going to be -2 times itself. So I'll really only get a +4. But we had in reality a +20, so that means I need an additional +16 on top of that. And now this denominator matches this denominator. And to make things even nicer, in our next line, we will rewrite that +16. So again, not touching the numerator yet, but we've got our s minus 2 squared, and I can rewrite that denominator, or that 16 as a 4 squared. So that's looking pretty clean so far. So let me erase this down here. But we found the appropriate terms that we needed to rewrite from this to cleaning it up to look like this. So what's next? we need to start worrying about this numerator now, because right now the numerator does not match the form that I'm looking for over here. I've got something that looks really similar, again, to what we have written down here in problem number 19, right? S minus a squared plus k squared. Here's some s minus some number squared plus some other number squared. But the numerator doesn't match the form of what I have in the parentheses up here. If this was an s minus 2 on top, we would be great. We would have it in the exact form that we needed, right? We'd have s minus 2 on top, and we'd have s minus 2 squared on the bottom, and it'd already be in this form. We don't have that. But my goal is to force that to be there, because I want it to match this form of what we're looking at. So I want to force an s minus 2 into that numerator. So let's do that. I'm going to force this f of s to look like an s minus 2 is up there. So let me just copy the denominator first. So s minus 2 squared plus 4 squared. There's the denominator. And the numerator, I'm going to force an s minus 2 up here. But I really have 3 s's. So let me keep that 3 here, and let me just write it as 3s minus 2. Even if this was 3s minus 2, it wouldn't be too bad, because remember, we can always pull that constant outside excuse me, outside of the inverse Laplace transform, and I'd have something that was transformable. So we're close, but this doesn't match what I have written here. If I were to distribute this 3 through, indeed I would get 3s, but I wouldn't get a plus 1. Instead, I'd get a minus 6. And so right here, I have 3s minus 6. That doesn't match 3s plus 1. How do I make up for that? Well, to make it identical, if I added 7 to this, now I do have 3s plus 1. So if you were to simplify this numerator, essentially what we're doing is we're unsimplifying it in kind of clever ways to force it to match the forms that we've got over here. So it's all algebra, but we're doing algebra in an uncharacteristic way. We're doing it basically backwards. We're unsimplifying things. We're trying to force factors out that don't actually even exist there. But now I've got it set up that we have it in the form that's really close to how we need things. Okay, so I have a 3 times s minus 2. That's not too bad. That looks a lot like this. And then the other piece, I have a constant. I have a 7 over this other piece. So what I want to do is now split this up again into separate pieces. The first piece, I'm going to pull the 3 out, and I'm going to write it as s minus 2 over s minus 2 squared plus 4 squared. So this is the first piece. I've now taken care of everything over here. The only thing I haven't touched is the plus 7. But because this appears in the numerator, I can just split this up into 2 separate fractions. Right now we have it written as one big fraction, but I can always split up if the numerator is made up of a sum of 2 separate pieces. I could write that as 2 separate fractions, and that's what I'm going to do. I'm going to write it as plus 7 over the same denominator, s minus 2 squared plus 4 squared. This piece is basically ready to go. This piece matches exactly what I have written right here. The only difference is I have a factor of 3 out in front, but that's fine. That factor of 3 can get pulled out, as we've already seen, outside of our inverse transform. This other piece looks very similar to the piece that I've got right here. Right? This piece leads to e to the at times the sine of kt, and it requires a constant in the numerator. But the constant here needs to match the constant down here. So for this to match exactly, I wouldn't need to have a 7 up here. I'd need to have a 4 up here. And so that's going to be our last step. Let me just copy the first piece. I'm not touching it. It's done. It's ready to go. But the other piece needs to have a 4 in the numerator. And how do I make up for that 4 in the numerator when it was originally really a 7? I can pull out basically a 7/4. Right, so basically we pull the 7 out, we need a 4 up there, so I had to multiply by 4 in the numerator here, but to counteract that 4 in the numerator, I also needed a 4 in the denominator. So this 4 cancels with this 4, and we're left with just the 7 that's really there. But we basically just have this constant now that's out in front of this piece, which is also ready to take the inverse transform of. So we're good to go at this point. We've got exactly what we need. We can think of this now as, so if we take the inverse Laplace transform of our original function 3s plus 1 over s squared minus 4s plus 20, that big ugly mess, well, that's the same as taking the inverse Laplace transform of this equivalent, algebraically equivalent expression that we've got right here. So in this case, that's the same as doing 3 times the inverse Laplace transform of the first part that we have here, so s minus 2 over s minus 2 squared plus 4 squared, plus 7/4 times the inverse Laplace transform of 4 over s minus 2 squared plus 4 squared. And these two pieces compute directly to give us our f of t, which is going to be 3. This one transforms according to this rule, line 19. K is equal to 4 for us. A is equal to 2 for us. So we're going to get e to the 2t cosine of 4t from that first piece. And then for the other term, we have a 7/4 sitting out in front of everything. And this one matches this one, line 18, with again, a being equal to 2, k being equal to 4. So that's going to be e to the 2t, right, e to the 2t sine of 4t. And there's the inverse Laplace transform. So there's our function f that we get out of that. All the work in this is in the algebra, finding clever ways to manipulate the algebra so it looks like something that appears in our table here. So that was our goal. So one thing that's going to come up a lot in these, when we're dealing with these denominators, where we're going to have to either complete the square or factor in some way, is we're going to come up with complicated messes like this that are ultimately going to require us to do some partial fraction, basically decomposition of our rational functions. So before we go much further, I want to do a quick review of some partial fractions. So we'll often need partial fractions. And so let's do a partial fraction review. Okay, so partial fractions comes up and has a couple of different cases that you can encounter. So let me just review the possible cases that we can get and see how we resolve each one of them. So the possible cases. One thing that can happen is we wind up with non-repeated linear factors. So case number 1, which I'm going to call non-repeated linear factors. So this would be an example where our f of s looks like this. So we're dealing with some sort of rational function, like the one that we just saw. There's some polynomial on top, and it's divided by some other polynomial on the bottom. And it turns out the different cases we're going to be interested in for partial fractions. So we're always going to be dealing with some rational function. Almost always the thing we're going to be concerned about with is how does s factor? And in this case, the idea is, sorry, not s, how does q of s factor, the denominator? In this case, if it factors into non-repeated linear factors, we're going to have one approach. So basically, if our q of s, the denominator, can be factored, this is going to get ugly, as the following. So if q of s can be factored as q of s equals s minus s1 times s minus s2 times s minus s3, and so on and so forth, dot, 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 all the way up to s minus sn, assuming that it's some nth order quadratic down here. where these numbers that we found, the S1, the S2, and so on. So where S1, S2, S3, dot, 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 Sn are all distinct numbers. So they aren't repeated. None of them are the same. Then it turns out that we can write the following. We write that our f of s, which again, we're trying to basically split it from the ratio of two complicated polynomials into a sum of a bunch of much simpler polynomials. It can look like this, or P of s over Q of s. Again, that's where we started. The goal is to have it look like this. We'll have some constant a1 over s minus s1 plus some constant a2 over s minus s2 plus dot, 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 up to an over s minus sn. So the numerators are all constants. And again, the idea of partial fractions, we're basically trying to undo taking a common denominator. So if Q of s is our common denominator, with these being all the different factors, we've undone that and split it up into a bunch of different functions that are each now have a linear factor for their individual denominators. And if we can split them up in this manner so that it looks like this, then notice each one of these individually looks an awful lot like line number 11. We'll be able to break this up into a bunch of just exponentials when we do our inverse transform. So that's one case that can occur. Non-repeated linear factors. And again, the a's are constant. So let me just make that totally clear. A's are constant. So those numerators are all just constants. Case number 2. Oftentimes, we're not going to get so lucky to have n distinct linear factors down here, and we might wind up with some repeated factors. So in this case, what happens if we have repeated linear factors? So in this case, same thing. We've got our f of s equals p of s over q of s, but what if q of s has a root with multiplicity of greater than 1? So if q of s has a root with multiplicity greater than 1, multiplicity of, and let's just say k. So k is greater than 1. And say the root that we're interested in is, say, the root is s sub j. Right? These other ones we called S1, S2, up to Sn. Let's say S sub j is the one that has this multiplicity. Then it turns out that we replace those terms, the terms involved with this Sj root, with a different factorization. So we replace those terms, that term's factorization, with the following. So it's going to look like we'll take, so Aj is the constant associated with Sj, right? So this is the first one that we'll look at. But we're going to write it as Aj1 plus Aj2, a different constant, but we're still associating it with the root j. But now we'll have s minus sj squared, and so on and so forth, all the way up to whatever the multiplicity is. So ajk would be the kth term. So if the multiplicity is 4, this would require up to 4 terms, where the denominator is now s minus sj to the 4th. In general, it's to the kth power. So we can keep constants in the numerator and just take basically every power of s minus sj up to and including the prescribed multiplicity. So if the multiplicity is 2, you just have these two terms. If the multiplicity is 3, you'd have these two terms plus one that involved another constant over this term cubed. And in general, we're going up to the kth power because k is the multiplicity, meaning k is how many times this term shows up. So we'll do some hard and fast examples in case this is still unclear. But for now, that's what we're going to be looking at. And then the last one is sometimes we can't even break down the factors to be linear factors. Sometimes, at best, they're quadratic factors. All those ones that we were having to complete the square on, those are quadratic factors, right? We cannot factor them in our normal method because they wind up giving us complex roots. So in those cases, we don't just force the factorization. Instead, we let them stay as quadratics. So the third case is, what do we do when we're dealing with quadratic factors? And so quadratic factors. So basically, if the q's that we're dealing with, if q of s has complex conjugate roots, which is, right, our complex roots always come in pairs of complex conjugates. If it has complex conjugate roots that look like, say, mu sub j plus I times eta sub j. Looks kind of like a v, but that's the Greek letter eta. So if that's one of the roots and the other one is mu sub j minus I times eta j. The point being, it's just a pair of complex numbers. I could have done a plus ib, but we've already kind of used a as these constants in the numerators. We're going to kind of try to do the same thing here, reserve a and b for what shows up here. So I'm just sticking to some Greek letters here. That doesn't really matter what they're called. But the point is we have a complex conjugate pair of roots. Then basically what we need to do is let our, essentially what we have is as factors that look like this. We have s minus one of these roots, so s minus mu j plus I eta j. If I take that and multiply it by s minus the other root, s minus mu j minus I eta j. So basically, this root is here, this root is here. This would mean s would be those roots, so I'm basically kind of like multiplying it out to see what we get. When you multiply this out, you wind up with something of the form that we were just talking about a minute ago. You wind up with an s minus mu sub j squared, so s minus mu sub j squared, and we can try this with real numbers in a little bit, plus eta sub j squared. You wind up with the completed square version of it, right? So you can basically multiply through by all of these terms, cancel stuff out, clean it up, and this is what this multiplication looks like. These are the types of things we were just dealing with right up here. Here's an example of one that had complex roots, and we basically just completed the square to find out what that denominator looks like. So that's kind of the idea here. We're doing that same thing. Get the roots basically into this completed the square form. So this is like our complete the square form that we need. So complete the square. But if these roots have some multiplicity, so they themselves are repeated. So if this root, or these roots rather, because it's a pair, if these roots are of multiplicity k. So basically you have a quadratic that's being squared or cubed. Then in this case, the partial fraction expansion of these terms is the following. And this is going to look hideous. It's less complicated in practice. I'm just writing these all out with all the horrible grid. So AJ1 times our S minus mu J1 plus BJ1 times eta J over our S minus mu J squared plus eta J squared term. So there's one of them. Plus plus all the way up to the kth term AJK S minus mu JK plus BJK eta J over S minus mu J squared plus eta J squared. Okay. All the way up to whatever the kth power is. So basically, it's kind of like the one that we just did, where you basically, our goal is to keep the numerator kind of the same relatively simple thing. Here it was all just constants. Here now it's basically a bunch of linear terms, right? So this is a linear term, right? It has an S in here. It's some constant, S minus some other constants plus some other constant. We've just got it factored in an ugly way, but this is really just a linear equation at the end of the day over our quadratic term on the bottom. But if that quadratic term has multiplicity k, so right, if it's like an s squared, whatever we just got, minus 4s plus 20 or whatever, but that's being squared, this thing, which we could break down easily, because we just did it, s minus 2 squared plus 4 squared. This is just the exact same example from the last problem. But now the whole thing is being squared, so our factored term is squared. So we basically do that denominator to the first power, then that denominator up to the second power, and so on, right? If this was a cube, we would need 3 of these things. We'd have a linear term on top, so basically you'd guess a linear term over this factored version to the first power, then you'd guess a linear function over this term squared, and then you'd have to guess a linear function over this term cubed for our last one, so all the way up to the power k down here. So again, this looks scary, but when we do these in practice, this will make more sense. So we will do some concrete examples of all of these cases to try to make this a little bit easier to swallow. So in our first example, let's say that we have, we want to, again, find the inverse Laplace transform of an f of s that looks like, I don't know, let's say maybe s plus 2 over s squared plus 3s plus 2. See if that works. Okay, so in this case, what we want to do is work on the denominator first. So our f of s, I'm going to start by just rewriting it, s plus 2 over s squared plus 3s plus 2. We can rewrite that denominator by factoring it. I'm looking for 2 numbers that multiply to give me 2, add to give me 3. And so I think this is going to be s plus 1 times s plus 2. And this doesn't look too bad. From here, I can see that basically we could either, well, that was inconvenient. Let's just, to make life easier. So at this point, we could just cancel these and go from there. We'd have 1 over s plus 1. It really is simpler than it looked, but let's pretend that we didn't have that. Let's pretend that I didn't make up a dumb problem from the get-go. Let me come back and change this number so we don't get just cancellation everywhere. So let's do s plus 3 in the numerator. And now there's no such cancellation to take place. So what we're going to do now is try to split this up into basically a bunch of separate terms. And we have some, again, different ways of doing that, but ultimately it boils down to partial fractions. I'm interested in trying to get this thing to look like something over s plus 1 plus something over s plus 2, right? So let's see, a over s plus 1 plus b over s plus 2. And I can do this because my factors on the bottom are distinct and linear factors. So this is our case 1 where we've got distinct linear factors down here. And so we've just set it up exactly like this. A over the first one plus b over the second one. So in this case, I want to basically rewrite this like this. We just need to figure out the appropriate values of a and b. And I should mention there are sometimes some other algebraic ways you can split things up like this. If you can come up with a clever way to split this up in the way that we're doing without having to resort to partial fractions, that's fine. But partial fractions is sort of the fail-safe method that we need here. So if I were to try to rewrite this back in this form, I would need to make a common denominator. And so what we would get is, in this case, I need to multiply this one top and bottom by s plus 2, and this one top and bottom by s plus 1. So we'd have, in this case, s plus 3 over our s plus 1 times s plus 2 term is equal to, we've got a over s plus 1, and I need to multiply that one top and bottom by s plus 2. No problem there. For the second one, it's b over s plus 2, and I need to multiply it top and bottom by s plus 1. Good. And so what we wind up with in this case is something that looks like on top, we wind up with, let's see here. So the denominators are all the same, so we just need to compare the numerators. When I compare the numerators, I'm going to get s plus 3 on the left is equal to a times s plus 2 plus b times s plus 1. And we can either distribute through and look at the different powers of s, so look at the s to the first power terms, and then look at the constant terms to try to solve for a and b, or we can just pick, in this case, convenient values. And this happens whenever we've got distinct linear terms. The easiest way to do it is just pick values of s that simplify the equation. This equation needs to hold true for every value of s, so pick ones that are convenient. So for example, if s is equal to -2, then on the left-hand side, -2 plus 3 gives me a 1 on the left, so -2 plus 3 gives me 1. And over here, the -2, when I plug it into this term, will make this 0. We won't have any a's, so I'll have basically 0a plus, when I plug in the -2 over here, we'll get -1, so b times -1. So what does b need to be to make this work? 1 equals -b, so b itself has to be -1. And if we plug in another convenient value, say -1, that's going to kill off this term. On the left-hand side, when I plug in -1, we will get 2, so -1 plus 3 is 2. And over here, -1 plus the 2 will give me a positive 1, so I'm going to have a 1a plus this one will give us a 0b. And so now I need to figure out what a is equal to, and according to this, a has to be equal to 2. And so we get an equivalent expression for f of s is 2 over, zoom out so I can see the whole thing, 2 over s plus 1 plus 1 over s plus 2. So 2 over s plus 1 plus 1 over s plus 2. And now we've got something that's in the form of our, oh, here it is, our exponentials. I just need to notice the numerator is 1 in both cases. This has a numerator of 2, so I'll need to pick that part out. But basically, we can rewrite this as f of s equals 2 times 1 over s plus 1 plus 1 times 1 over s plus 2. And that implies when we take the Laplace, inverse Laplace transform, So essentially what we're doing is applying the inverse Laplace transform. We should get f of t equals, for the first one, it's going to be 2 times, what's the equivalent? What does a have to be to match this? Well, it's s minus a. Here I have s plus 1, so I have to think of this as s minus a negative 1. So a is a negative 1 in this case. So in this case, we're going to get a 2 out in front, and a is equal to negative 1 to get it to match this form. So e to the negative t plus, for this form, there's a factor of 1 out in front that we didn't even bother to write. Right? It's just the same as this anyways, and the value of a needs to be negative 2. S minus negative 2 would match this form. So we're going to have a plus e to the negative 2t. And there is our f of t, having done our partial fractions on that one. So that is the easy case, when we get nice linear factors in the denominator. And they're distinct. What happens if we get repeated factors? So let's take a look at that. So let's say that I wound up with something that we recognize to be the following. So again, let's find the inverse Laplace transform of our f of s, and let's say that our f of s looks like this. I don't know, some number, let's do 3 again, and maybe we've got an s minus 1 times an s plus 2 squared. In fact, let's make it clear. Let's do it as s squared plus 2s plus 1. There we go. Let's do that. Okay, so here is the function that we're dealing with. We want to find the inverse Laplace transform. It has this factor of s minus 1. And then over here, if I were to factor this, I would recognize this as s plus 1 squared. So our f of s, in this case, can be rewritten as 3 over s minus 1. It has one real distinct factor in the denominator, but the other one is a repeated one. It's s plus 1 squared. It's of multiplicity 2. So the factor s plus 1 appears twice down here. So how would we split this one up? So again, we need to do partial fractions. And the way that we would do this is similar to what we did here. So our goal is to guess the correct form. Can we guess the correct form that this should take? For any distinct linear factor, so this one's distinct, we can guess simply a constant over that number. So a over s minus 1. But for a repeated one, we have to guess a couple of different things. There's different ways to do it. The easiest one is to guess a constant over that number plus another one where we guess a constant over that same denominator at the highest multiplicity. One way that people sometimes bypass this is, instead, if you have a quadratic term on the bottom, you guess a linear term on the top. That's another way to do it. But again, this is just the way that I prefer to do it. There's more than one way to skin this cat, as the saying goes. I don't skin cats. But if we were to, there's more than one way to do it. And so this is the way, according to the write-up that I gave, of how you would do it. So real distinct term gets its guess right here. And then the repeated term, the one that has multiplicity 2, you guess a constant over that factor plus a constant over that factor raised to whatever power we're going up to. So if it was cubed, I'd have to guess yet another one, a d over s plus 1 to the third power. But the nice thing about it is it keeps all our powers, or all our numerators, as constants. And that's going to be kind of nice because it allows us to, again, use things of this form in general, where the numerators are constants. We're going to wind up with stuff in a lot of cases that looks like number 16 and 17 here for these types of scenarios, because we're going to, again, have constants over these denominators, constants over a denominator raised to some power, over a binomial in the denominator raised to some power. So that's what we're looking at here. So how would we do this one? Again, the idea is pretend we were finding the common denominator. So we would write these out as we know that 3 over s minus 1 times s plus 1 squared has to be equal to this term. I need to multiply top and bottom by this s plus 1 squared. So I'd have a over s minus 1 times s plus 1 squared over s plus 1 squared. For the middle one, we have b over s plus 1. I need to multiply it by a factor of s minus 1 over itself and another factor of s plus 1 over itself. So I need an s minus 1 over s minus 1. And I also need a factor of s plus 1 over s plus 1 to get this to match. So I'll have an s plus 1 squared and an s minus 1. Toss some parentheses around that one. And then the last one, we've got our c over s plus 1 squared already. To get its common denominator, we just need the s minus 1 factor over itself. So now these all have the same denominators. We compare the numerators to force them to be equal. And when we compare the numerators, we've got on the left, it's 3. And on the right, we will have a times s plus 1 squared plus b times, s minus 1 times s plus 1. And the last one, we got plus c times s minus 1. And again, we can FOIL these out if we want and group all the s to the second power terms, group all the s to the first power terms, and group all the constants and solve the equations that way. Or we can try our luck with the approach that we did last time. The approach that worked last time is great when you have distinct linear factors, but when we have these repeated linear factors, it's not going to be able to work. We're not going to be able to find 3 sort of magic numbers that kill off all the terms every single time. But we can find a couple. I can find s equals 1. If I put s equals 1 in, it'll kill off this term and leave me only a. If I plug in s equals negative 1, it'll kill off this term and leave me only c. And then by the time we get to our last one, we'll be able to kind of fudge the other results together to figure out what the last number should be. So I'd suggest kind of picking and choosing. We can use kind of both approaches. So in this one, I'm going to say if I let s be equal to positive 1, that's a convenient number. On the left-hand side, we'll still have a 3. On the right-hand side, this term, when I plug in s equals 1, I'm going to get 1 plus 1, and we're squaring it. So 1 plus 1 is 2, squared is 4, so I'm going to get 4a. When we plug in the 1 here, it goes to 0, so we have plus 0b. That kills off that whole term. And when we plug in the 1 here, it kills off that term. And so we also have plus 0c. And so what this tells me is that in this case, a has to be 3/4. If we plug in s equals negative 1. So again, the left-hand side is 3, right? It's just a constant anyways, no dependencies on s anywhere. But we're plugging in negative 1. If I plug it in here, negative 1 plus 1 is going to be 0, so I'm going to have 0a. If I plug in negative 1 to this term, it's going to kill off this whole piece, making it 0, so we're going to have plus 0b. And then the last term, when I plug in negative 1, we're going to get minus 2c. And so what this tells me is basically that negative 2c is equal to 3. So we divide both sides by negative 2, and we'd get that c equals negative 3/2. So we found 2 of the values that we need. Now that I have those 2 values, we can go and figure out what the last remaining value is, so b, doing a number of things. We can go back and basically plug these values in and kind of compare and contrast, or we could even try to just plug in some other value of s. Sometimes this works and can make life a little bit easier. So for example, if I just did s equals 0, 0 is always a nice number to plug in. This is another option. Even though s equals 0 doesn't kill off any of these terms, we don't need it to kill off any of these terms because I already know the value of c and of a. This is the only piece we don't know. So if we just plug in s equals 0, then on the left we'll have 3. Over here, plugging in 0 is nice because I just get 0 plus 1 squared is still 1, so I'm just going to have a. Over here, we're going to get b, plugging in 0, I have a -1 times a +1, so it's going to be a negative b, so minus b. And then over here, plugging in 0, we get a minus c. But I already know the values of a and c, so what this tells me is I really have 3 equals a, which was 3/4, minus b, which is the one thing we don't know, minus c, but c is -3/2, so minus -3/2. And now we have an equation for b. So basically, I'm going to subtract 3/4 from both sides, and that'll kill off that term. I'm going to subtract off, right, because this minus and negative can be thought of as plus or positive, so I can subtract 3/2 from both sides. If I subtract 3/2 from both sides, that kills off this term. What do I get out of this? So 3 minus 3/2 would leave me with 3/2, minus 3/4 leaves me with 3/4. I get that 3/4 equals negative b, which tells me that b is equal to -3/4. And so I can go plug all of those in. So basically what I did is just literally, I did them in my head, but you can just subtract off these two numbers from the 3. You'll get 3/4. And all we were left with on this side was the negative b. So what we get when it's all said and done is this form with these values of a, b, and c. So f of s is equal to a, which is 3/4 over s minus 1. So 3/4, I'm just going to pull that out in front. 3/4 times 1 over s minus 1. Might as well just pull it out in front. The next one is b over s plus 1. b was -3/4, so I'm going to get minus 3/4 times 1 over s plus 1. And then the last term was c over the s plus 1 squared, and c was -3/2. So let's do -3/2, 1 over s plus 1 squared. So here is our f of s. These two terms are ready to go. They look exactly like the form that we've got here, and this one looks very similar to the form that we've got right here. And so that's what we're going to get. If this is what f of s is, then this implies, if we again apply our inverse Laplace transform, we're going to get that f of t is equal to 3/4 times, what does this piece transform back to? So in this case, a is equal to a positive 1, 1 over s minus 1, so that's just an e to the t. Then I have minus 3/4 times the inverse transform of this piece, which looks exactly like this, letting the value of a be -1, so e to the negative t. And then lastly, we've got this minus 3/2, 1 over s plus 1 squared. That looks like this term right here, where again, a is equal to -1. So that looks like t e to the negative t. And there is our f of t that we get in that case. So in this case, a combination of some non-repeated factors, some repeated factors. This is how you do that. Let's do one last example. Even though we've kind of already done these, of the quadratic form. For our last example, let's try this one. So again, we want to find the inverse Laplace transform of an f of s that in this case looks like, let's say, I don't know, just 20 over, let's say s times s squared plus 2s plus 10. So this is what we're trying to find the inverse transform of. So our goal is just to algebraically kind of tear this thing apart using our partial fractions rules. So in this case, my f of s term, which is, let me just copy it down, 20 over s times s squared plus 2s plus 10. Our goal is to factor this term in the parentheses. If you try to factor this using the quadratic formula, for example, you'll find out that it does indeed have complex roots. This is one that we need to complete the square on. And I can tell that because if I pick the number that would give me the first two terms, so if I kind of break this apart and write it as 20 over s times, the number that I'm going to get here is going to be an s plus 1 squared. When I do s plus 1 squared, that will give me the s squared plus the 2s that I'm looking for, but it'll also give me a plus 1. So this thing is s squared plus 2s plus 1, but I don't have s squared plus 2s plus 1. I have s squared plus 2s plus 10. And so that means I have an additional 9 left over. So again, if to get to this, you have to first actually try to factor this using the quadratic formula and find out that you get complex roots, that's totally fine. But basically, what you'll find when you do that is that the complex terms show up in these two positions. And so we have to complete the square to basically set up this denominator. So this is what we're looking at. To go on from here, our goal would be to split this up again into pieces that show up in our table over here. And so in this case, I want to rewrite 20 over s times s plus 1 squared plus 9, which I'm going to rewrite as 3 squared. I'm going to rewrite this function as a couple of separate pieces. First, we have a linear piece that's just going to be a over s, because this is a linear factor that is of multiplicity 1. And then I have this quadratic term that also is only of multiplicity 1 at least. At least I don't have like a squared out here or something like that. But it's going to require us to kind of do a little bit of extra work. So let me just write the denominator again. It's going to be s plus 1 squared plus 3 squared. And our rule, if we go up to wherever it was, back here, in this case our multiplicity was only 1, but this is the numerator that we have to guess then. It's basically a constant times s minus whatever, that same shift that we saw, plus b times whatever number showed up down here. And let me make it clear why we can do this. So basically, we wound up with a quadratic term in the denominator. We need to guess a linear term up here, but instead of just guessing this, so we could do this, we could do bs plus c. But that's going to be a little bit inconvenient. It'll work, but it's going to require more work than putting a little forethought in. And here's the idea behind the forethought that I want to put in. To get this inverse transformed, I need to spot what it corresponds to over here. And the ones that I'm looking at are these two functions right here, where there's a shifted version of s squared plus some k squared. So rows 18 and 19 in our table. But to do the inverse transforms, they require us to either match the numerator k with the value down here in the case of sine, or match the numerator s minus a with the shifted s that shows up in the denominator. So instead of just guessing bs plus c, I'm going to guess b times the s plus 1. And by doing this, I'll already have the s plus 1 that I need in the numerator. Once I solve for b, whatever b happens to be, I'll have something that looks like s plus 1 over s plus 1 squared plus 3 squared. I'll have something that matches this form exactly. And similarly, instead of just guessing plus c, I'm going to guess plus 3c, because as soon as I find c, I'll already have the 3 in the numerator that I need to match up with this example right here. So basically, the idea of what was suggested up in our hints for the partial fractions is to basically already get the pieces that you want to show up in the numerator to match the pieces that show up in the denominator. So this is what we're looking at. So now our goal would be to basically find a common denominator on this. This first one needs to be multiplied top and bottom by this denominator. This one needs to be multiplied top and bottom by this denominator. And so we will get, in this case, a over s times our s plus 1 squared plus 3 squared over s plus 1 squared plus 3 squared. So top and bottom. And then our other term, just finish copying it here, needs to just get multiplied top and bottom by s. And at this point now, all of these terms have the same common denominator as this, so I just need to compare the numerators of these two pieces. So if we compare the numerators, on the left-hand side, we're going to have 20, and on the right-hand side, we are going to have this big old mess, so a times, the easiest way to do this is we could go back to the unfactored version if we want. We can leave it here, but remember, it's equivalent to what we have written here. And whatever, for now, I'll just leave it like the way that it's written, the factored version. But a lot of the times you can save a little bit of work here if you just immediately go back to the unfactored version. And I'll explain why in a minute. And over here we have b s plus 1, and can't forget that we were multiplying this by s, so times another s plus 3c times another s. And the reason that we might want to basically expand this back out is because in this form, it's not going to actually be very effective to plugging guesses for s, specific values. Whenever we have these quadratic factors, the method of basically picking specific values of s isn't going to work because I can't pick a specific value of s that'll make this term go to 0. The whole point is it doesn't have any real roots, so I can't pick a value of s that'll make this quadratic 0 because it has complex roots. And I don't want to be guessing complex values of s. That just makes life extra miserable. So there's no real numbers s I can pick that'll 0 this out. This is the only one that I can pick a convenient value of s to kill some stuff off. So let's do that first. So I'm going to let s be equal to 0, and that'll give us a little bit of leeway. But we have three unknowns here, a, b, and c, and that means we're going to need three equations down here to eventually solve for that. We can use a combination of picking some convenient values and or looking at the different orders, and we'll do the different order version in just a minute. So I could plug in s equals 0, and that's a little bit convenient because plugging in s equals 0 at least kills off all of these terms. And I'll wind up, you can see this term and this term, for example, they'll both die, and I'll just have this piece over here. So I'll have that 20, which is what we get on the left-hand side, is just always 20. And when I plug in 0 on the right-hand side, I'll get 1 squared, which is 1, plus 3 squared, which is 9. So 1 plus 9 is 10. We get 10a. And this immediately gives us that a is equal to 2. And again, these two terms both died off because s was equal to 0. Alternatively, we would want to actually FOIL everything out over here and look at all the different terms of each order. And so if I can get this all on the screen at once, foiling this all back out, or expanding this back out, will eventually get us to this quadratic. And that's why I was suggesting sometimes it's easier if you just jump straight to this quadratic. So we'll have a times s squared plus 2as plus 10a, right? That's multiplying the a through to all of these terms, the a through to all of these terms. Over here, we'll have, when we multiply this out, I'm going to get an s squared plus s, both of those times b, so I'll get plus bs squared plus a bs. That takes care of these ones, and then plus 3cs. And so now we can collect all of the quadratic terms, so all the terms that involve second powers, all the terms that involve first powers of s, so here's an s, here's an s, here's an s, and then all the terms that involve only constants, so that's just this guy here. And we could do it that way. So this is the other way. Let me just pretend that we had never done this way. What we would do is what I call, again, the big O notation. I will look at all the things that are of order s squared, Then I want to look individually at all the things that are of order s to the first power, and then all the things that are of order s to the 0th power, or basically order 1, all the constants. So this is another, again, if you're not familiar with this notation, it just means we're looking at all of the things that kind of are of that group. For two polynomials to be equivalent, right, on the left-hand side we just have a constant, on the right-hand side we have a polynomial. For two polynomials, 20, a constant, is a 0th order polynomial. For two polynomials to be equivalent, every single coefficient has to match. So the s squared terms have to match, the s terms have to match, and then the constants have to match. And so we can break it up in that way. Even though it looks like one equation, it's really encoding three separate pieces of information. One about how the order s squared terms match up, one about the order s, and one about the constants. So let's take a look. The order s squared terms. So what are the terms on the left-hand side of our equal sign that are proportional to s squared? There aren't any. So we have 0 s squareds on the left-hand side. And on the right-hand side, see if I can get this all on the screen at once. Good enough. So no s squareds on the left-hand side. On the right-hand side, we have as squared plus bs squared. So I have a plus b s squareds on the right. For the next one, order s. So on the left, again, we have 0 s's on the left. There's nothing proportional to s on the left. But on the right, we have 2a s's plus bs plus 3 cs's. So 2a's plus 1b plus 3c's. And then for the last one, the constants, the order 1 terms, so all our constants, on the left we have a 20. And on the right, the only constant that we have that shows up, that's an s squared, there's an s term, s squared, s. The only term that we have is this 10a term. So 10a. This gives us the same equation that we got back earlier when we plugged in s was equal to 0 up here, the one that we crossed out. So we could have used this piece instead of this piece, and it would have given us the same information. So as long as we use 3 of these pieces of equations, even if we're mixing and matching using some plugging in values of s, using some where we're looking at each sort of order of magnitude, any combination that gives you the equations you need will work. So this one is enough to give me that a is equal to 2. As soon as I get a equals 2 from that one, that tells me that this equation now tells me that 0 is equal to 2 plus b. So what does b have to be to make that work? Well, what plus 2 gives me 0? Negative 2 plus 2 gives me 0. So b has to be negative 2. And now that I have both a and b, we can now come to this equation to solve for c. So this equation now tells me that 0 on the left is equal to 2 times a. So 2a is 2 times 2 plus b, which we just found was negative 2, plus 3c. And that's equal to 0. So now we can solve this one. We've got 4 minus 2 is going to be 2. So we've got 0 equals 2 plus 3c. We can move either the 2 over to the other side or the 3c over to the other side, whichever one we want, and figure out what the value of c has to be. In this case, it's going to have to be c equals 2/3 with a negative sign, negative 2/3. Let me make that negative sign a little more apparent. Negative 2/3. So negative 2/3 for the value of c. And when that's all said and done, we get that our f of s, the thing that we're trying to inverse transform, now takes, where is it? Which ugly form? It takes this form right here with this value of a, b, and c. So the first term is just a over s, but a was 2. So I'm going to just write that as 2 times a 1 over s. So that is, get it all on the screen at once, that's taking care of this term. The next term is going to be this one, the b times the s plus 1 over everything. So what did we find for b? It was negative 2. So let me just write that as minus 2 times s plus 1 over s plus 1 squared plus 3 squared. That is this part of the numerator and the whole denominator. And now we need the last part of the numerator and the whole denominator. This one was a 3 c. So basically we need the value of c, which we just found to be minus 2/3. So minus 2/3. And that allows me to leave the 3 in the numerator that we wanted there anyways. So minus 3 over s plus 1 squared plus 3 squared. So there is that term, right? Again, c is the negative 2/3, but I intentionally forced a 3 to appear here ahead of time so that I'd have the numerator that I wanted so that it would match this form here. So I forced the 3 there anyways, and that gave me a c of negative 2/3. And so now each of these is easy to inverse transform. By design, I've kind of set them all up to be easy. Let's start with this 1 over s. We'll go up and recall that 1 over s inverse transforms back to just a constant, 1. So this implies that if we apply the inverse Laplace transform, it implies that f of t is going to just be the number 2. So this one gives me just 2. Right? 2 times the inverse transform of 1 over s, which is just 1. This one gives me minus 2 times this form. That inverse transforms to, that's this form right here, the e to the at cosine kt, where for us, our value of a, to match these two up, a needs to be negative 1, and k needs to be 3. So the next one is going to be minus 2 e to the at, where our a is negative 1, so e to the negative t, e to the, come on, e to the, even that's ugly, e to the negative t, zoom in a little more, e to the negative t cosine of 3t, right? The a was 3, and our k was negative 1, so that goes to there. Sorry, other way around. The a was negative 1, the k was 3. So right, there's our k, and right here is our a. Just so it's totally clear. And the last term is minus 2/3. The inverse transform of this piece, the 3 over everything, that's this one. So same thing, e to the negative t, but now sine of 3t. And so there is our inverse transform in this case now of one of the examples that has some partial fractions done on something that has one of these quadratic, non-factorable, non-irreducible terms that we can't factor. It's stuck as a quadratic, and we have to complete the square. And it gives us results like this. So again, this is a lot to absorb. It's really ultimately all algebra. And once you do these, you start to kind of be able to anticipate which form to expect. But you're going to be using a lot of the same forms over and over and over again. There's going to be a lot of these ones that are exponentials mixed with sines and cosines, a lot that are exponentials by themselves, some that are polynomials times exponentials. These are the types of things that we've seen in our solutions in the past. They're the things that we're going to anticipate will come up in our solutions going forward as well. So after this, after we get comfortable computing Laplace transforms and inverse Laplace transforms, the next thing we're going to do is apply this to a whole bunch of problems. And we're going to actually solve some differential equations using this technique.